Great, so please keep telling us where you're from, telling us where you're from, and big welcome to everyone to this talk today. It's a webinar organised by the Space Universities Network. And the Space Universities Network is not an organisation for students, it's an organisation for teaching staff of UK universities. Excuse me, so we're trying to support the space higher education community, but by supporting the staff, we're hopefully supporting the students. And I know we've got a lot of students attending today. My name is Lucy Bautu. I'm Professor of Space and Systems Engineering at the University of Bristol. And my colleagues, Dr. Kate Smith from Manchester and Ian Raper from UCL, run our chairs of the Space Universities Network, ably assisted by our coordinator, Charlie Leach, who you can see on your screens at the moment. So what is SUN? Just very briefly, we basically provide resources and events to the staff who are teaching space science and engineering. So if you think one of your staff members is not a member of SUN, do encourage them to join. We have 39 universities and 93 members, and we have a website. And we provide all sorts of information for those staff. We do actually have a few pages which are general, which will signpost you on to outreach and careers resources, but we also have a big resource bank for those staff who are wanting to improve space science and engineering teaching in the UK, to make the UK into one of the foremost space countries in the world. So with that fanfare of an opening, I'm going to pass over to Charlie.
Hiya, and welcome to the first SUN Space Industry webinar of this academic year. We're lucky enough to have Sam here talking to us today. The webinar will be around 50 minutes. It will start with a presentation from Sam. There will then be a short interview with him, and then time for you guys to do a Q&A. So as he's talking through, remember to put your questions in the chat. Sam is a senior thermal engineer based at RAL Space, part of the UK Research and Innovation. A graduate of the University of Southampton, Sam has a broad range of experience in thermal design, analysis, and testing of spacecraft instrumentation. His past and current projects include the spectral imaging of the coronal environment, SPICE, instrument for ESA's solar orbiter, and the mid-infrared instrument on NASA's James Webb Space Telescope. He also has experience in cryogenic test facilities and CubeSat thermal design. His talk will introduce types of tests and spacecraft, and will introduce the test that spacecraft must pass before it is ready to launch, along with the challenges that brings. Examples of the test campaigns conducted by RAL will be explored, such as cryogenic testing of James Webb Space Telescope instruments. Thanks, and now I'll pass on to Sam.
Thanks, Charlie. Just give me a moment to set up. Just realised I need to be sharing sound on this, ideally. Sorry, one moment, everyone. I will just kick this off. So yeah, thank you for the introduction from you both. So really for this webinar, I'm going to give a bit of a crash course really on testing for space. I'm going to start by introducing who we are as an organisation and how we fit in to the wider space community. I'll then talk about why testing for space is so important and some of the challenges that it brings before moving on to the different types of tests that we do at our facilities, as well as some examples of some projects along the way. So first of all, who are we? Well, we're based at the Rutherford Appleton Laboratory in Oxfordshire. We've got an image of RAL here. We're mostly in RAL Space based in this building, which we call R100, and houses the bulk of our existing facilities. We also have some older facilities here on this corner of site. We're part of the wider laboratory operated by Science and Technology Facilities Council, who operate a number of large facilities. This big sort of donut-shaped facility is Diamond. We also have the ISIS facility at the back of site. And we're part of Harwell campus, which is actually one of the main space clusters in the UK at the moment. This building is a European Space Agency building. There's a satellite applications catapult building here, ESA Business Incubation Centre here, and there's a whole host of different startup companies that are now joining Harwell and developing the space community here in the UK. We're also currently building a brand new facility, which it's out of date, this picture, but it's currently being built here, called the National Satellite Test Facility. I'll talk a bit about that in a moment, but in RAL Space, we're approximately 300 or so staff, and we have a mission objective, which is a mission statement, I should say. We're the UK's national laboratory to advance the exploration of space and the environment for the benefit of all. So just to explain a little bit more about us as an organisation, I mentioned that we're part of the Science and Technology Facilities Council. We, along with the other 6 research councils and Research England and Innovate UK, form UK Research and Innovation. And then UKRI, along with organisations such as the UK Space Agency, the Met Office and the National Physics Laboratory, form part of the Department for Business, Energy and Industrial Strategy. So yeah, we're publicly funded, and we're really there to bridge the gap between industry and academia, and to stimulate economic growth within the UK through our contributions to science. So in terms of RAL Space, what does that mean? Well, our main activity is in designing and building space instruments, working alongside space agencies such as ESA and NASA to develop payloads for missions. We're also heavily involved in research, defining those mission concepts using our scientific expertise in areas such as astronomy and solar physics. We're heavily involved in technology development. Pretty much every project that we do involves the development of novel ideas, new technologies. So that's a big part of what our engineering staff are involved in. Data and information, taking the data from satellites and making it accessible to the wider scientific communities. Facilities, this is really the topic of the talk today, so I'll talk a bit more about that shortly. And economic impact, as I mentioned before, UKRI. So this could be through spinning out companies based on the technologies we develop, getting involved in public engagement, events like this today, talking to the next generation and getting them interested in STEM. And then also training, so through things like our graduate training scheme and our apprentice scheme, training the next generation of engineers that are going to have the impact on the space industry that we need them to. So before I move on, I mentioned a few slides ago that we're currently building the National Satellite Test Facility, or the NSTF. So I thought it was worth adding a slide here just to give a bit of context to that. It's a £105 million government investment that aims to provide the UK space industry with a one-stop shop for the complete environmental testing of spacecraft. So you've got this image, I think, is from earlier this year of the building as it looks at the moment. This is the big new thermal test chamber that's just been added to the building. I'll talk a bit more about that shortly. But really what this facility does is it complements our existing facilities, larger scale thermal, vibration, shock test facilities, a brand new acoustic test facility, EMC facilities, antenna measurement, and then also mass property measurement. So I'm going to talk a bit more about this later on, but just to introduce the NSTF and the fact that it's a really exciting time to be involved in the space industry in the UK. So yeah, let's talk about testing then. So I think before we get onto the specifics, it's worth clarifying why this is important and why we care about testing. And the key to understanding that is to consider the space environment. It's probably quite an obvious statement, but without the Earth's atmosphere, we've got to withstand an incredibly hazardous environment in space. So this obviously is going to depend on the exact mission, the exact orbit, and the environment it's going to work in. But typically it has to be designed to withstand large mechanical loads, things like vibrations, acoustics, mechanical shocks. extremes of hot and cold temperatures. If we think about the International Space Station that we can see in this image, which orbits the Earth roughly every 90 minutes, it goes throughout its lifetime of having a series of incredibly sharp extremes of hot and cold that it's got to withstand. And then there's a few other areas. So intense radiation, microgravity, space debris. These are maybe things that we wouldn't specifically test for in our big facilities, but we've got to make sure that we design our spacecraft with these kind of restrictions in mind. And as engineers, our main concern is ensuring that everything that we design and build is going to be able to both survive and, more importantly, operate to the required performance throughout the orbital lifetime. And to an extent, we can do this through computational models. So we can use these models to assess the environmental conditions, and we can analyze within those environmental conditions to get an idea of what performance we're going to see. So an example I've got on the slide here are some thermal models. So these were built using actually these three were built using ESA TMS. This one was built using Systema Thermica, which is typical thermal engineering analysis for space. So it's these kind of models that will give us an idea of what kind of temperatures we're going to expect with the mission that we're designing for. But a really key point is that these models aren't perfect. There's going to be errors in them because there are certain things that we don't know, we can't quantify, and of course there's going to be an element of human error. And then even if we've got a good idea of what the temperatures are based on these models, we've still got to check that the design, once it all comes together, is going to be able to still stay in one piece as it goes through those temperature extremes. So this really emphasizes the importance of testing on the ground. And in terms of those tests, our challenge is to simulate that environment as realistically as possible, which is why test facility design is such a big industry. We start early on through a project lifetime by building and testing a prototype model. If this passes the test successfully, that then gives us the confidence to move on and build the flight model. Sometimes also we would take lessons learned from that preliminary round of prototype testing to implement within the flight model. And then with the flight model, we again repeat the tests to confirm the suitability. A key kind of mantra that we work to is once the hardware is in space, we can't fix it. So it's much better for us to fail a test on the ground first and understand what's gone wrong prior to sending it into space and it failing there, because once it gets there, if it fails, in most cases, there's not a lot we can really do about it. So again, this last point, probably a bit obvious. Space missions often cost billions of dollars and have to last years or sometimes even decades in space. So these tests are a really critical part of justifying that and giving us the confidence it's going to work. If you think of the James Webb Space Telescope, this is the Otis optical telescope assembly for James Webb being tested at NASA's Johnson Space Clean Array. I mean, JWST is a $10 billion mission, and it just wouldn't be workable if we weren't able to test to this level. So one other point, just to emphasize the challenge, we have to do all of our work in clean rooms. Contamination can have a number of detrimental effects on our spacecraft equipment. It can damage optics. It can reduce the reliability of our hardware, things like mechanisms and electronics. So we have to do all of our work in these ultra clean environments with these rooms that continuously circulate the air and scrub out the contamination from it. We have a number of clean room facilities at RAL Space, ISO class 5 being our kind of cleanest areas, but we also have ISO class 6 and ISO class 7. So the air in these rooms, I'm talking thousands of times cleaner than the air that we're currently breathing. So they do a really good job of scrubbing that contamination out. But we, of course, as humans are the biggest contaminators, so we have to do all of our work in these clean room suits. So yeah, this requirement for cleanliness, again, presents an additional challenge. I'd say particularly with thermal testing, we've got to make sure that it's all being done in a clean environment and we're not making our spacecraft dirty in the process. Okay, so let's move on to some testing. So I'm going to start by talking about thermal testing, which is, as a thermal engineer, the area I'm most knowledgeable about. We've got a range of thermal vacuum chambers in RAL Space, ranging from the very small all the way up to this 7-meter diameter chamber, which is the one that we're building as part of the NSTF at the moment. We saw an image of a few slides back. This chamber we can see here is a 5-meter chamber. We've actually got 2 of them in R100. And there's really 2 types of tests that we would do in these chambers. The first one is something that we call thermal vacuum testing, where we thermally cycle our hardware between a range of temperatures that we would calculate based on our analyses. And this gives us the confidence that it can survive and operate across those temperature extremes over a number of different cycles. The second one, I would argue, is a bit more interesting. It's called thermal balance testing. And the purpose of this test is that we allow our hardware to settle on a steady state condition. And we do this for a number of cases, and we compare the data from our test with what our thermal model has predicted. And if we thermal analysts have done our jobs well, then we don't have to make many changes. If we've not done our job so well, we have to make several changes to our model. But the key thing is that we've done this test, which has told us that, and we can then improve our data or prove our analyses and our thermal analysis predictions for the actual flight itself. So to give you an idea of the capability of these chambers, the RAL panels have a network of liquid nitrogen pipework behind them. So they can go as cold as liquid nitrogen, so around the sort of 80 or 90 Kelvin mark, up to as hot as typically about plus 150 degrees Celsius using heaters. And then we can achieve vacuums within these chambers of less than 10 to the minus 5 millibars. So incredibly high levels of vacuum that we achieve during these tests. But every test is very different according to the mission. And these tests are long and can sometimes last for months. On these next couple of slides, I've just got a few examples of some, I would argue, slightly more interesting tests to show you. I think I've actually got I didn't think this through. I've got to go back to this to be able to play it. So this is a video of the Solar Orbiter spacecraft undergoing solar testing. So this wasn't actually at RAL Space, this was at IABG, but we contributed the SPICE instrument to Solar Orbiter, so we were involved in the completion of this test. And what we can see is there's a solar lamp shining on the spacecraft from the direction of the infrared camera, and the spacecraft is gradually rotating to simulate an orbital maneuver. And it seems very fast. This is actually minutes, this scale in the bottom left. So it was actually a very slow process, but this kind of data for this particular scenario was needed for us to be able to try and characterize the impact of the sun during this solar orbiting mission. If I move on from that, we've also got a slide here about some cryogenic testing that we did years ago now for the mid-infrared instrument on JWST. So in these circumstances, as I said, these RAL panels can only cool to about 80 or 90 Kelvin. So what we had to do was develop an additional facility that could slide inside the thermal test chamber and allow us to cool beyond that. And then we did this using a set of cryogenic coolers, which cooled this shroud to about less than 40 Kelvin, 35, 40 Kelvin. And we also had areas of the instrument that we had to cool down to 6 Kelvin. So we had to design a bespoke solution for this. And as an aside, we're actually currently developing a similar, although much larger, about double the size of this facility for the aerial mission. So yeah, really the key point here is actually the design of these facilities is almost a project in itself. We have to work for years and years on the design of them, working alongside the instrument and the spacecraft teams in order to make sure that at the point where they're ready to do their testing, we're going to have a facility waiting for them that can do it. So let's move on to mechanical testing. So vibration testing, first of all. So this is using something that we call a shaker table to vibrate the hardware and simulate the incredibly violent vibrations that we would see on a typical rocket launch. We can see the panel here that it's mounted to. So this panel, I'll show you a video of this in a moment. The panel will move horizontally. And then we've also got a panel just behind here, which you can't quite see in the picture, but it will move vertically. So we'll mount it for that, mount it to that for the vertical axes. And yeah, we'll mount accelerometers to it to monitor the response while it's shaking, and that will detect any anomalies that might be caused by the vibrations. To give you an idea of how powerful this is, the table at RAL, so this table we're looking at the moment, can simulate accelerations as high as 140 Gs. Obviously, the heavier the item you put on that, the lower that is. And probably for most hardware, we test between something like 10 or 20 Gs, depending on the exact launch specification. And then also with random vibrations up to 2 kilohertz. So when we see that in action, so this is the bit that might be a bit noisy, so hopefully you can hear that. But yeah, you'll see this in action now. This was vibration testing for the Spire instrument that we built for the Herschel mission. It's a bit of an older mission, this, a bit of an older video. I think this really emphasizes the power of this utility. So you'll see that this, I believe, is a random vibration test with that. And you'll see the frequency gradually increase, and you get to the point where it'll almost appear as though that's the point where the train motor. It's a little bit before my time with project, but I suspect that the mechanical perhaps a bit worried about what was going to be going on. This is the case, obviously, looking quite closely before anything. I suppose we never normally see really aggressive failures. Only very subtle changes. Really okay, another type of mechanical testing is Pyroshock testing. So this is actually a very new facility for us at RAL. I think we opened up for our first customer last year. This picture is testing our first customer's hardware. The reason we do this is that during the launch, there can often be a number of aggressive shock events that are caused by separations of rocket stages. Also, when we're in space, there can sometimes be similar shock events caused by things like single shot mechanisms deploying. And what these do is they create a jolt through the spacecraft and through our instruments that we have to make sure that we can survive. So to give you an idea of how this works, so this is a test item here mounted to this platform, and then this mounts to this big plate here, and then there's a tube at the back here. So I'll show you a video of this. Basically, this tube is this tube here, and this panel here is this panel here. So we're kind of seeing the reverse of this. And I'll play this. It's only 10 seconds, but I'll replay it again in a moment. We have a compressed air system that drives a bolt through this chamber that then impacts on the panel at the end and creates the jolt through the panel that then shocks the hardware itself. So obviously this is done in a very controlled way, and again we use accelerometers for monitoring the event and making sure that the shock that we're generating is suitable. But yeah, a new facility for us here at RAL, and something that I think we're still kind of building up at the moment. And I'm just going to finish just by talking about a few other types of tests. So these are facilities that we're currently developing as part of the NSTF. I kind of briefly mentioned them before. The first one is acoustic testing. So this is actually a picture of some early demonstration tests of the acoustic facility. So it probably doesn't look very scientific, but what we've got is our hardware in the middle, surrounded by these enormous speakers, which are used to generate an acoustic field and verify that our spacecraft can survive the vibrations caused by those acoustics. We're also developing an electromagnetic compatibility, or EMC, facility. So this is a picture of some of the early build stages of that. So this is the copper floor being laid. It's essentially a Faraday cage that your hardware would go inside, and you would use this facility in order to measure the electromagnetic properties of your spacecraft. You might ask why that's important. The reason for that is we need to make sure that, particularly for science missions, you might have science missions with something like a magnetometer on it, which is measuring magnetic fields. You need to make sure that the electromagnetic interference from your spacecraft isn't disrupting those scientific measurements, or at least that you're able to characterize the magnetic field being generated by the spacecraft. And that's what these facilities are there to do. Also, within the same facility, we are going to be having the capability to measure the performance of antennas, which is critical for lots of different communication systems on satellites. And then finally, I couldn't find a good picture of this, but we're also developing a facility for measuring the mechanical properties of spacecraft, so specifically center of gravity and moments of inertia. And this is so that we can verify the consistency of the built hardware with the design requirements. And they're also quite important inputs for things like the launch vehicle and even things like vibration testing as well. It's important to have a good idea of where your center of gravity is on your hardware. Right, so this is my last slide. I just want to finish by flagging up some useful links for you all. First of all, we've very recently launched a new virtual tour of our R100 facilities. This actually only launched a couple of weeks ago, so it's really exciting to be able to tell you about this today. You can see roughly what it looks like here. You can go on it and you can select different areas of R100 to go and visit, and you can learn more about it. So, for example, some of the big test chambers that we saw, and then also the vibration facility here is here as well. So by all means, do go and check that out. We've also, on the 1st of December, got a early careers conference that we're hosting at RAL Space. It's completely free to register. You just got to go on the link there and register your interest. And yeah, there's some really good speakers this year, so please do go ahead and check that out. And then finally, we've also got our recruitment campaign at the moment for our next intake on our graduate training scheme. So this is for graduates that will be starting in 2022. There are careers at RAL Space there, but there's also careers across the whole of STFC. So not just on the space science, but also in other areas of physics and scientific computing. So yeah, if you're looking for graduate roles at the moment, then please do go and check that out. And yeah, that concludes my talk. Thank you all for your attention this afternoon, and back over to you, Charlie, now, I think.
Lovely, that was great. Thank you very much, Sam. Would you mind quickly just briefly going over the vibration testing again? Because I think we struggled to hear you as you were playing the video.
Oh, okay, sorry. Yeah,
if you mind, yeah, that'd be brilliant.
Yeah, that's what I thought. Yeah, I'll quickly go through that again. So what I can maybe do actually is just play it with the sound muted. Yeah, I kind of debated whether to include the sound, but I thought at least you get an idea for how noisy it is, and what kind of stuff you would hear if you're in the room with it. But what we're seeing here is vibration testing of the Spire instruments, which is part of the Herschel mission. And this is quite an old video, this, as you can maybe tell from the video itself. But what we have is a random vibration cycle with the frequency gradually building up. We can see the accelerometers coming here from the hardware itself that are measuring the performance of it during test. Yeah, another point I made was the fact that the mechanical engineer at this point is looking quite closely at this area of the instrument. It's a bit before my time, this project, but I suspect that he was maybe particularly worried about that interface in terms of his mechanical analyses that he'd done, and maybe wanted to monitor it a bit closely. And yeah, I think the last point I made was just about the kind of failure modes that we might get during these tests. So sometimes when we show this facility to people in person, but they'll ask, okay, do you get things flying off the hardware and shooting across the room and stuff like that? It's never that exciting, or something's had to go very badly wrong with the mechanical is that exciting. It's normally very subtle changes in the response of the hardware, which you would be able to capture on the accelerometers. So you'd see a very subtle change in the response that would indicate that something had gone wrong, and it would normally perhaps be something like a bolt coming loose, or maybe an area of the instrument deforming in a way that it shouldn't have done, and that kind of thing. So yeah, that was everything on this slide. Sorry about that. I'll bear that in mind.
No, that's brilliant.
When I show this video, that it can be a bit noisy to hear me.
No, that's great. So now we have some more general questions that were submitted prior to the webinar. Anyone that's in the audience can submit questions into the chat, and then we'll do those at the end as a bit of a Q&A. So if it be possible, could you give us more of an overview to your role itself at RAL Space, and a look at your day-to-day like program sort of pre and post-COVID, if it's changed during that as well?
Yeah, absolutely. I mean, it has changed post-COVID because there's a lot more homeworking now, but we're still throughout COVID doing these big test campaigns, and we're still as needed on site to build our instruments and to do the testing that we need. So yeah, I'm a thermal engineer. I guess there's bits of this that I covered during the talk, but my role is to make sure that what we send into space is going to be able to both survive thermally and then also to meet the kind of performance requirements given to us by people like the systems engineers and the mission scientists. So that could be something like maintaining a certain level of thermal stability on a detector or something like that. It could be achieving a certain temperature that's needed. I showed the MIRI instrument before, where we have a requirement for that to keep the detectors as cold as 6 Kelvin. So that's a kind of typical requirement that I would have to deal with. It's a very collaborative process. So I would say thermal, out of many of the other engineering disciplines, there's a lot of awareness that we have to have for lots of other disciplines. It's kind of a systems role in some way. We have to have an awareness for things like the electronics dissipations and the kind of power management, obviously the mechanical design, how feasible it is to mount things like thermal hardware and radiators, that kind of thing, multi-layer insulation. And then, yeah, also things like optics as well. So it's certainly very varied. And I think I spend a big portion of my day in kind of design meetings with people, and then based on those design meetings, doing things like analyses. And then obviously the test part as well as part of that at the end.
That's great. Could you also give us a more of an overview on how, well, your sort of education and how that led up to your role at RAL Space?
Yeah, so yeah, I grew up, I guess, very interested in maths and science. Ended up studying aerospace engineering at the University of Southampton. And then for my 4th year master's, I specialized in spacecraft engineering. But I would say, to be honest, the space stuff was something that I kind of fell into a little bit. I mean, when I started my degree, I didn't immediately think of space as a potential career opportunity, if I'm honest. I think this is hopefully something that's changed now in the kind of 10 years since then, 10, 15 years since then. But I didn't necessarily think that the UK was that involved in space and that it would be something for me. And it was only through doing my university studies and learning more about it that I understood that those options were available. So yeah, I kind of just fell into it a little bit, really. I developed a passion for it at university, and then I was fortunate enough to get recruited by RAL Space as part of the graduate scheme.
Great. Could you also tell us a bit about how the industry itself has changed during your career, and also where you see it heading in the next sort of 15 to 20 years, if possible?
Yeah, so I think the first thing is the scope of it, first of all. So when I was graduating from university, there weren't so many recruiters in the space industry, if I'm honest, at least at a graduate level, or certainly nowhere near as many as there are now. So I think for a start, there are far more opportunities. I mean, I'm just going to jump back through my slides. Even if we go back to the campus picture here, one big way it's changed. I mean, this building wasn't here when I started. This building wasn't here when I started. This building wasn't here when I started. We've had all of these different space organizations spring up over the last 10 to 15 years. So yeah, the scope of it certainly changed. I think also there's been a kind of move, I would say, towards things like CubeSat technologies as well, is another big thing. 10 years ago, I think CubeSats were mostly a kind of a student thing, you know, a kind of, yeah, perhaps a kind of introduction to space, whereas now CubeSats are becoming more and more prominent. We're getting more and more CubeSat launches every year. I've recently started working on a project called CubeMap, which is an ESA CubeSat mission. So what we're seeing is almost a kind of miniaturization of technology and an increased sophistication, or increased level of sophistication in terms of what we're able to do with these CubeSats. We're doing more and more incredible scientific payloads now for these CubeSats. So I think that's another really exciting area of growth. And I think there's a lot of organizations, startup companies, that kind of thing that are springing up in order to exploit that.
That's great. So we can take some questions from the chat as well now. So we have one on software. So what software do you use to make models and also test both static and dynamic loading experienced through launch? And also, what software do you use to study thermal and radiation environments?
So, so there's a few questions there. I'll start with the thermal stuff first. So we tend to use a piece of software called ESATAN TMS. So it stands for European Space Agency Thermal Analysis Network. And it's the kind of ESA standard for thermal analysis of spacecraft. We also occasionally use a piece of software called Systema Thermica, which is an Airbus software. And yeah, it's a finite difference software. So it's, at least I found when I started using it, it was a bit kind of different to what I had got used to when I was studying at university. But yeah, they allow you to analyze in a range of different orbits. Yeah, they're certainly a lot more sophisticated now than they were 10 years ago. In terms of the mechanical analysis, I think different organizations use different softwares. We tend to use finite element analysis software, so using software such as ANSYS, software such as NASTRAN. NASTRAN, I think, is a more kind of space-focused one, but we have a team of mechanical engineers that do that analysis. And then they also sometimes use that software as well for things like thermoelastic analysis. So we have to work closely with them, feeding them the temperatures that we get from our analyses for them to do their thermoelastic work. I think there was something else in there as well, wasn't there? There was a radiation analysis was another one. Mm-hmm. So yeah, I've got to confess, I'm not 100% sure what the answer to that is in terms of the radiation analysis software that we use, but I know that Systema, which is what we use for Thermica, so that's one of the thermal analysis softwares that I mentioned, that also does have a module for radiation analysis. So these softwares, what they will normally do is they will calculate what the radiation environment is in a given orbit. And then as engineers, we've got to confirm that the components that we're using on our spacecraft are going to be able to survive in, or be able to operate in those that radiation environment. And we might have to go out and do things like radiation testing and that kind of thing. Yeah, hopefully that answers the question.
Yeah, I think that's great. So I'll make the links available to everyone. Will receive an Eventbrite message basically saying thank you for coming, and I'll attach the links and also a feedback form in that message. Could you tell us a bit about what the most challenging aspect of your role at RAL Space is?
Yeah, it's a good question. I think my answer to that would be sometimes it's a challenge that is so varied. So I'm quite fortunate really to work on quite a range of different projects. So I've worked on solar instruments such as SPICE, cryogenic instruments such as MIRI, CubeSat design, electronics management, cryogenic facility design. Sometimes I would say it's quite a challenge jumping between different projects and having to kind of get into a different kind of thermal mindset to tackle them. And yeah, I mean, I would say also another big area of challenge sometimes with working in the space industry, and this is a kind of more general thing rather than a thermal specific thing, is that we have to heavily document absolutely everything. So every bit of design work that we do, every test that we run, every design that we put together, we've got to have a very clear document trail for what we've done with that hardware. So again, this comes down to, if something goes wrong in space, we've got to be able to go back and try and understand what's gone wrong, and the more information we've got to do that is the better. So the kind of the product assurance side of it, I think is a bit of a challenge, but it's a very necessary challenge.
Right, so we've also got a question about how do you test the satellite systems interacting with charged particles and going through the Van Allen radiation belt?
That's a good question. So I think that there are specific facilities that are available to do that. I mean, a lot of the time with these kind of considerations, it comes down to things like electronics components and that kind of stuff. So one of the requirements that we have is using space qualified components. So components that either have heritage on previous missions that have had to work in a similar environment, and have had a very kind of thorough campaign of qualification tests, which I imagine for a mission that passed through the Van Allen belt would consist of having some kind of testing in a kind of environment with charged particles. So it's all done through, again, this comes back to the kind of product assurance stuff that I mentioned, making sure that the components that we select are qualified for that environment. We wouldn't do a kind of test of the kind of full spacecraft at that level, because it's more at the kind of component level that we're worried about in that instance.
Okay, great. Yep, so just also to let everyone know that the recording and slides will be available on our website afterwards. We have a final question, I think, and that is, if you were able to talk to yourself just before starting out on your career, what advice would you give your younger self?
Yeah, it's a good question. I think first of all, trying to explore new ideas earlier. I mean, I mentioned before in my previous answer that space was something that I fell into quite late. So I kind of wish that when I had been at a kind of younger age, sort of secondary school level, I'd been a bit more kind of focused on what I want to do and that kind of thing. I think in terms of so I suppose that's probably not relevant to many of the audience who are past that point, but certainly at the kind of university sort of age, I mean, attending events like this is a really fantastic thing to be doing. And again, that's something that I probably didn't do enough of when I was at university. So trying to take on board new ideas and trying to learn as much as you can. I personally didn't do anything like a kind of internship as well, which I really wish I had done. So I think if you get any opportunities to gain new experiences and to meet new people and to develop those contacts, then you absolutely should do. And I think that's the advice that I would have given myself at that kind of age.
Lovely, thank you very much. I think unless there's any questions that I've missed in the chat, I think we can draw the webinar to a close. Thank you very much, everyone, for coming, and thank you very much, Sam, for speaking to us today.
Thank you very much. My pleasure.
A huge thank you on behalf of Sun, Sam, and a big round of applause from the audience, I'm sure. So
okay,
thank you so much. Thank you everyone for coming. Do come to our next webinar. We've got lots more exciting ones planned for you, so keep an eye out in your emails.